Welcome to The Explainer. Today, we are getting our hands dirty with computational geometry. And look, we're not just going to be memorizing a bunch of formulas. We are building a powerful, code-friendly toolkit that's going to let you solve some really complex geometry problems. This is an absolute must-have if you're a competitive programmer or a CS student who really wants to nail those exams. All right, so here's the game plan. First, we're going to start with a tricky little area problem that trips a lot of people up. Then we'll build out our geometric toolkit and really focus on the superstar of that kit, the cross product. After that, we'll see how to apply it to real problems like intersections and polygons, and we'll wrap it all up with an exam prep guide to make sure you're ready to go. So let's kick things off with a problem that seems super straightforward on the surface, but hiding in plain sight is this classic trap. It's something that's really easy for us as humans to see and avoid, but it's incredibly tricky for a computer to handle unless you tell it exactly what to do. This is really where computational thinking starts to shine. Okay, picture this. You're in an exam and this question pops up. What's the very first thought that comes into your head? For pretty much everyone, the instinct is to break this weird four-sided shape into something we already know how to deal with. And yeah, this is the intuitive way to do it, right? You just grab two corners across from each other, slice it down the middle, and poof, you've got two triangles. You can find their areas with something classic like Heron's formula, add them up, and you're golden. Simple, logical, and it works. Well, sometimes. The whole thing falls apart the moment you run into a concave shape, one with a dent in it. In that case, our simple, intuitive method doesn't just fail, it fails spectacularly. And this right here gets to the absolute heart of the problem. A computer doesn't have our eyes, it doesn't have our intuition. If it just randomly picks two opposite corners on this shape, the diagonal it draws might be completely outside the polygon. And that's going to give you a wildly wrong answer for the area and a big fat 0 on that exam question. We need a method that works every single time. So let's build a better way, a foundation for solutions that are actually robust. To write elegant code for geometry, we first have to figure out the best way to represent our points and vectors. And the first tool we're putting in our toolkit is the complex number. Now, you might remember these from math class with the imaginary eye and all that, but for us, just think of it as a perfect little container for a 2D point. The real part is our x-coordinate and the imaginary part is our y-coordinate. Simple as that. And now for a seriously cool programmer shortcut. C++ has a built-in complex class that's perfect for this. With a quick typedef, we can give it a nice short alias, like p for point. Then, with a couple of macros, we can get the coordinates with just p.x and p.y, instead of typing out p.real and p.imagine. It seems like a small thing, but trust me, when you're writing dozens of geometry functions, this makes your code so much cleaner and easier to read. All right, now for the absolute star of the show, the cross product. Seriously, in 2D geometry, this is not just some formula you memorize for a test. You need to think of it as a question you're asking two vectors. Hey, which way did you turn? Now, the formula itself is pretty simple. x1 times y2 minus x2 times y1. But its geometric meaning is what makes it an absolute powerhouse. It lets us solve a huge range of problems without getting bogged down in messy special cases. So here's the magic. The sign of the cross product tells you everything you need to know. Imagine you're walking along vector A, and then you have to turn to walk along vector B. If the cross product is positive, you just made a left turn. That's counterclockwise. If it's negative, you made a right turn, clockwise. And if it's 0, no turn at all. You're just continuing in a straight line. Okay, so now that we have this amazing turn detector, we can start elegantly solving a whole bunch of classic geometry problems. This is where we stop talking theory and start looking at real exam-style questions. I mean, just look at how versatile this one operation is. Checking if a point is on one side of a line or the other? Yup. Figuring out if two line segments cross? You bet. Even calculating areas and distances? The cross product is the fundamental key that unlocks all of these. It's like a Swiss Army knife. Let's take that line segment intersection problem. How do we solve it with our turn detector? Well, two segments cross each other if and only if the endpoints of each segment are on opposite sides of the line made by the other segment. We can check this with just 4 cross-product calculations. It's a clean, robust test that lets us avoid dealing with messy slope-intercept equations, which means no division and way fewer floating point headaches. Okay, let's see how these fundamental tools can scale up to solve even bigger problems. We can now finally solve our original quadrilateral problem the right way and even tackle more complex things, like any polygon and different ways of measuring distance. So remember that tricky concave quadrilateral from the beginning? The shoelace formula is its worst nightmare. It's an elegant solution that works for any simple polygon, whether it's convex or has dents in it. You basically just walk around the vertices, taking the cross product of each adjacent pair, you add them all up, and then you take half of the absolute value. This formula completely dodges that whole which diagonal do I pick problem. So what if you need to check if a point is inside some crazy, complex polygon? There's a beautifully simple algorithm for that called ray casting. It's just like it sounds. You stand at your point, you shoot a ray, like from a ray gun, in any fixed direction, say straight to the right. Then you just count how many times that ray hits a wall of the polygon. And here's the rule. If you hit an odd number of walls, you're inside. If you hit an even number, you're outside. It's an incredibly clever and robust method. It's also really important to remember that distance doesn't always mean one thing, especially in exams. You'll probably see two types. Euclidean distance is the one we all learned in school. It's the straight line path, as the crow flies. But Manhattan distance is the distance you travel in a city grid, where you can only move up, down, left, or right. It's absolutely critical for any kind of grid-based problem. Now here is a pro-level tip that can save you a ton of time on an exam. Manhattan distance problems can sometimes be a pain, but check this out. If you rotate the entire coordinate system by 45 degrees, a point xy transforms into a new point x plus y, y minus x. And in this new rotated world, the Manhattan distance just becomes the maximum of the difference in the new x and new y coordinates. This can turn a complicated problem into something much, much simpler and faster to solve. Okay. Let's pull everything we've learned together into a practical guide. Think of this as your cheat sheet for revision. It's got the key things you need to remember on exam day, so you don't lose any easy marks. Here are the non-negotiables. These are the core formulas you absolutely have to know by heart. The cross product, that's our turn detector. The triangle area is just a direct application of that. The shoelace formula scales that up to any polygon. You also see Pick's theorem here, another handy tool for finding area based on integer grid points. And of course, make sure you know your Manhattan distance. And finally, let's talk about the nasty programming traps that can absolutely ruin a perfectly good algorithm. First, never, ever use a double equal sign to compare floating point numbers. Always check if their difference is less than some tiny number, an epsilon. Second, your cross products can get big fast. Always use long for your coordinates to avoid integer overflow. And finally, always think about the edge cases. What happens if points are in a straight line? What if segments just touch at an endpoint? Handle those. And there you have it. We've covered the theory, the core tools like the cross product, and the strategies for your exams. You now have a solid framework for thinking about and crushing computational geometry problems. The only thing left to do is practice. So you've got the tools. Which problem are you going to solve first?